Today we will continue to study the Fourier transform properties about the differentiation and integration. Here is the differentiation properties. So dx over dt, we take the differentiation, but we know that the xt inverse Fourier transform, the xt are given 1 over 2 pi, and taking integration from minus infinity to the infinity, and xj omega, that's the Fourier transform of xt. xt Fourier transform has xj omega, and take the inverse Fourier transform of this one, and taking integration over omega. So this one is the inverse Fourier transform expression. We just take the differentiation with respect to time. Then this part given as a dx of dt, and look at here, this one is not function of time, it's a function of time t. So j omega is a coefficient of the t. So j omega comes out of the exponent, and this one is constant with respect to time. So the differentiation are given in that way. So this can be expressed as this way. This one is a derivative of x. So the Fourier transform of x prime are equals to j omega times xj omega. So we can compare that one. X prime t is represent the time derivative term of xt. Okay. X prime t. X prime t means dx over dt. So the differentiated the function transform are just multiplying j omega. So you can think about the d of dt are equals to j omega. So in case of differentiation, we can consider d of dt are corresponding in the spectral domain, it's just j omega. So in the spectral domain, it's j omega. Here shows that d of dt x equals to j omega times x function Fourier transforms. So another one, you can express that one. Fourier transform of this one is a j omega times integration of xt. So if you take the derivative of this one, that will become the xt. So we talk about the Fourier transform of differentiation. Here is an example for sine function. The sine function defined as this way. If t is positive, then it is plus 1. If t is negative, then it is minus 1. You can compare sine function with a unit step. If you multiply add 1 to the sine function, then in time is positive case is 2, in the negative case is 0, and divide by 2 equals the unit step function. So this equation shows the relationship between unit step and a sine function. And consider the half of the sine functions. Half of the sine function is unit step minus 1.5. The other way, unit step function is decomposed. The one is 1 over sine function, 1 over 2 sine function, plus 1.5. So this one means that the unit step has some offset value. Unit step's offset value is 1.5. But in sine function, didn't have the offset. Okay. By taking derivative of unit step equals to delta function. Okay. And it means by taking derivative with respect to the time is this one. So 1.5 times that sine function derivative equals to unit step function. And its important thing is the sine function has no offset terms, no DC terms exist. It's very important when you consider the differentiation. When we take the differentiation, any constant terms are cancelled out. It means by taking the Fourier transform of this one, du over dt equals to 1.5, okay, 1.5 times d sine function t over dt. But this part is removed. So it shows that it doesn't matter how much offset are added. By taking derivative with the respective time, it should be 0. So anyhow, this one equals the delta function. So this is the delta function. During this differentiation, these constant terms disappeared. So we can add any kind of number. But the sine function didn't have any DC component. It means a sine function, you can see here, it looks like this one. If t is positive, it's 1. If t is negative, it is -1. So average value is 0. Okay, so there is no offset in the sine function. So you can think about 1.5 times the sine function derivative equals to delta function. So here shows that this one means the delta function. Delta function take the Fourier transform, then it's 1. And also we can replace the d of dt as a j omega by use of the differentiation relationship. So we know that the sine function Fourier transform equals 1 over j omega. And if we take the sine, you have to multiply both of sides by 2. Then sine function are given like this way, 2 over j omega. So if you replace omega with a 2 pi f, then you can have this result. So we talk about the Fourier transform of sine function at here. To derive that one, we use the differentiation property of this one. Let's consider for the unit step function. Unit step function can be expressed in this way. By use of sine function, we can express unit step in such a way. But unit step has some offset terms exist here. By taking the Fourier transform of this one, we just taking the Fourier transform of a sine function. Okay, sine over 2. And then we need to take the Fourier transform 1.5. Because unit step consisted of these two functions. So by taking the Fourier transform, you know what? Fourier transform of sine over 2 equals 1 over j omega. So this part gives 1 over j omega terms. And what about the constant term? Constant term gives a delta function. You know what, that the constant has a 2 pi times delta omega, and the scale factor is 1.5. This is value k. So the unit step function Fourier transform are given in this way. We already derived how the unit step Fourier transform of unit step function are given. Is given. So it consisted of two different components. One is a sine function, the other one is a constant term. So sine function gives 1 over j omega, but the constant term, it is DC component. So this constant means the 2 pi times delta omega, but the scaled 1.5. So we have this result. Next, consider that the rectangular pulse. Rectangular pulse are defined like this way. This one can be understood in this way. The rectangular pulse t over tau are given. Okay, let's plot that one. Looks like this one. Okay, all the way 0. So this is 1. This one is 1 tau over 2. This one is minus tau over 2. So the width is tau. Okay, height is 1. So that's this function. The same function can be understood by use of the unit step one. Look at here, unit step is shifted minus tau over 2. So that is this curve. Okay, this is this curve. And okay, what about this one? Minus unit step t minus t over tau. The minus means that the opposite directions. T minus tau over 2 means time shift over tau over 2. So this curve shows this kind of function. Okay, so by a superposition that one, the final pulse shapes are given like that one. It's the same as this one. So this one is a rectangular pulse. Rectangular pulse can be decomposed into two different unit step functions. Okay, we know that the rectangular pulse of this one should have a sinc function like that one. So this is the Fourier transform for the rectangular pulse. We would like to find out by use of this unit step function transform. We know that the unit step function as shown here, that this one is a unit step Fourier transform. Fourier transform of unit step are given like this way: 1 over j, that's come from the sine function, and the pi delta omega is come from the constant terms. So Fourier transform of unit step are given like that. Then you know that Fourier transform is a linear operator, so we can apply one by one. So apply first unit step and the other one. Then this one is time shift terms are given phase change like that, and the unit step converted in uj omega. Similarly, the time shifting terms are given like that, and the unit step is given like that. By factorize, we can express the unit step times e to the j omega tau over 2 minus e to the minus j omega tau over 2. It means that the common factor is uj omega, and in that case here e to the j omega tau over 2 and the minus e to the j omega minus j omega tau over 2. So this part equals to 2 times j sine omega tau over 2. Okay, this is it. So it can be expressed in this way, but the j omega, uj omega can be given like that: 1 over j omega plus pi delta omega. Okay, this is what that one. So if you multiply this one times 1 over j omega, will give this result. What about this one? You can think about that this part becomes real number, but this one becomes the imaginary terms, 2j times sine delta. But the product of delta and sine, you can think about the delta omega can be expressed in this way. This is omega axis, and this function can be expressed in these approximations. This one is delta over 2 minus delta over 2. So this width is delta, the height is 1 over delta, then the area is 1. It's satisfied delta omega d omega minus infinity to infinity equals to 1. So the area is unit, so this area is 1. But what about these sine terms? Sine term, in the very short period of time, this delta is very small one. We need to take a delta as a 0, approach to the 0. Then sine function looks like this one. So by producting, this part becomes a positive number, this becomes the negative number. It's balanced out. So this product will vanish out. So only 1 over j times 2j times sine omega tau over 2 are remained in this way. We take the Fourier transform of a rectangular pulse by use of the unit step, shifted unit step function. In the shifted unit step functions, we can get the Fourier transform of a rectangular pulse. Next example looks like this kind of ramp signal. The xt is defined if t is -1 and 1 period, then it's changing from -1 to the 1. So slope is 1, and the other times it's always 0. So it follows this kind of the curve, 0 and step down and increase with a slope 1 and a step down and 0. So we would like to find out the Fourier transform of this one by use of differentiation property. By taking time derivative of this function, will give these shapes. If t is not -1 and 1 point, then derivative value is 0, and here also 0. So 0 and 0. 1. T is in between -1 and 1. Its slope is 1. So it follows this curve. So that's the rectangular pulse. And at the t equal -1 and 1 point, it's a step down change. The step down change, both of them. So because of that, there is two different delta functions are shown here. So at t -1 is delta t plus 1. That's this point. And delta t -1 is this point. So derivative of xt can be decomposed into these functions. We would like to find out the Fourier transform of this one. So we want to know xj omega. So to find out that one, we would like to Fourier transform of this derivative one. Before that, I would like to mention that the xt didn't have DC component or the offset component. I mean that by taking -infinity to infinity, x of t dt are equals to 0. So what does this mean? I would like to show you that the Fourier transform are given, looks like this one, t times dt. But I would like to replace the omega with the 0. Then this becomes the 1. Okay? Then it's this one. So DC component means x0. x0 r0. So there is no DC component that is that here. Okay? Keep in mind this property. If signal didn't satisfy this one, it's not possible to using these techniques. By taking derivative xt, after that we take the Fourier transform, then the result should be equal j omega times xj omega. And the Fourier transform of this derivative is consisted of three functions Fourier transform. So rectangular pulse Fourier transform, as we know that it's given these functions. Okay. So the area is 2. The first null occurs, and the width is 2, so 2 pi over 2 is pi. So that's this one. And delta function give the exponential 1, and this is t -1 is this one. So Fourier transform of this derivative are obtained like that. And we can find out xj omega are given by dividing 1 over j omega over 1 over j omega times Fourier transform of this derivative are given in this way. You know what, that this part is 2 times cosine omega. Okay, that's this part, and divide by j omega, we have this result. That's the Fourier transform of this wave, this pulse shapes. The next, we would like to study about the integration property. Or we would like to study about the Fourier transform property for integration. Fourier transform of differentiation are given by j omega times the Fourier transform of xt, as we have studied. Then what about the integration of this one? And just dividing 1 over j, it looks like this one. Is that satisfy these conditions? That's the questions. It means that the same thing can be understood like this way. If it's satisfied, Fourier transform of xt, okay, Fourier transform of xt will satisfy 1 over j omega times Fourier transform over dxt over dx dt. Is that satisfied? But we use that one over here. Is that valid for all case? It's not that one. The precondition is this one. If DC component is not exist, then this satisfied. This is working. By the integration of xt, it's this one. And the integration of x are given like that. This is the same relationship, but this one satisfied only this function didn't have DC component. Adhere that the left side is derivative. It removes any constant terms. DC terms are removed by taking derivative. That's why it is not valid when DC component is not 0. So here is defined that integration function of a, we have to take integration from minus infinity to t. Okay, this is defined as a function y. And then we can understand that this operation as a convolution between x tau and the u tau, t minus tau over d tau. That's the convolution of xt and the ut. The Fourier transform of impulse function is 1. So let this one is a gj omega. I mean that the delta t, take the Fourier transform gj omega, and the value is 1. In the time domain, it's a delta function, then the Fourier domain is just a unit. By taking the integration of impulse function, it becomes a unit step function. Okay, so by taking the Fourier transform, unit step function are given uj omega, but the delta function is 1. So we need to consider that these terms, xj omega at this moment is, this one is 1. So 1 over j omega are these terms, okay, from here. And the second term, so we have to consider pi times x0 times delta omega. x0 is minus infinity to infinity delta t dt is the DC terms. We know that by definition it should be 1, so it gives pi delta omega. And also we know that the delta function is a derivative of a unit step function. By taking the Fourier transform, we can use that the j omega times uj omega. So it is this one. So if you multiply omega times 1 over j omega, it's a 1, and j omega times this one. In omega equals 0 cases, it looks like this one, j0 times delta omega are 0. Okay, so it satisfies the derivative property. So we talk about the properties of differentiation and integration for the Fourier transform. Actually, we would like to study about Parseval's relationships. The energy of xt signal can be obtained by this taking square integrations. Absolute value square integration will give the total energy of the signal. So that's expressed by the e to the x, e over x. Okay, and the absolute value square can be understood in this way. In general, xt is complex number, then xt times x conjugate, that will give absolute value square. So by taking the integration is the energy. From here, xt is replaced by the inverse Fourier transform definitions. Inverse Fourier transform of xj omega given like this way, 1 over 2 pi times, and xj omega e to the j omega t times d omega is the inverse Fourier transform of the xt. And x conjugate is over here and dt is here. So the next step, we would like to change the integration sequence. D omega integrated later, and we would like to integrate with respective time first. So dt is here. So e to the j omega t, and xj omega t conjugate is here. But this one is not function of time, so we can push that back into outside of the integration bracket. Then it will give this integration is over here, and x conjugate x is here, e to the j omega t is e to the minus j omega t, and the conjugate. You need to consider this conjugate operator. Then this part becomes xj omega conjugate. So we can product xj omega times xj omega conjugate and take the integration with respective to omega and 1 over 2 pi. So it gives 1 over 2 pi times the integration of absolute square of xj omega and taking the integration. So let's compare the first equation and the last one. The first one is the total energy can be expressed in the time domain, absolute value square in the time domain, and taking the integration will give the total energy of the signal. But in the same value can be obtained by taking the absolute square of spectral contents of x and to take the integration over the whole frequency. So because of this one, x absolute value square is expressed is called energy per unit time. And in the spectral domain, absolute value square xj omega over 2 pi is called energy per unit frequency, or energy spectral density. If you would like to measure the energy confined in a specific spectral band, it means that we would like to find out the energy in between these two frequencies. Then we just taking integration from minus omega to the omega 0 will give the energy. This energy means that the energy contained in these frequency region. Hausbach's theorem says that the energy can be found from the time domain, or the same energy can be found in the spectral domain. It means that during the transform, the energy is conserved.